Hi, my name is Harry Hu. This is Lab 5 Magnetic Braking with Faraday, Physics 2212. So in the introduction, so in this lab we are asked to collect data on a magnet falling through an aluminum tube in order to observe and use Faraday's law. So we're first going to mark the north pole of the bar magnet. We're going to use an app to just drop the magnet through the tube and observe how long it takes to get to the end. We're going to be able to calculate the time it took for the magnet to fall through the length of the tube with a recording, and then we're going to repeat the experiment 5 times and calculate the average just to get a summary of the results. Just to note that it is not made of ferrous metal. So some key ideas: we have Faraday's law, Biot-Savart law, Ohm's law, Luke's magnetic force, the EMF formula. Our experiment time was 1.25 seconds. Our computational time was 1.12 seconds. So this is our experiment model. It's going to take some time for you to look at it, but basically it is a dipole model. We have a negative charge on the left and a positive charge on the right. And it's going to be going through the negative charge, through the positive charge, back around to the tail of the negative charge, and it's coming out the head of the positive charge. So in our experiment, we have just, again, the details: dropping the magnet through a loop tube 5 times to see how long it takes to travel. Assume air resistance is negligible and only 2 forces are acting. Our system is a magnet and aluminum tube. Surroundings is everything else besides that. So our measurements: we have tube length as 0.30 meters, aluminum foil width 0.01 meters, inner radius is 0.02 meters, outer radius is 0.03 meters, magnet mass is 0.03 kilograms, and our average fall time will be 1.26 seconds. So just to check one question: so why can't we use a ferrous tube? So ferrous tube, like a steel tube, contains iron, so it's going to interfere with the magnet, and we're going to get an incorrect result because of that. So what happens to the magnet? How is it compared to a magnet falling in free space with no tube? So it's going to fall slower than the one we tested because there is no opposing forces acting on it like with the tube's force, and so as a result we're going to get a different answer or result. So this is our Glowscript code. It's giving you some time just to look at the code to see what we did. So this is our Glowscript model. On the left we have the model that our code created, and on the right is our graph that was formed as a result. So in our discussion, our model differences. So our model was fairly accurate, and we used a virtual model, but we may have had some human errors while doing it. Our source of error is that our calculations may have been off, and we may have had some potential rounding errors. So the question is, what if the resistivity of the conductor was reduced as close as possible to 0? How will the dynamics of the falling magnet change? So if this happened, we probably would have a magnet not falling down and staying still because of that. And what if the holes were cut into the tube? How would it affect the ring currents in your model? So it would probably go faster because there would be less force opposing it. So thank you, and have a great Thanksgiving.